Cargo Math. Welcome back again. We have another marvelous adventure in the world of Topic 6. We are looking at 6.4 6-4 geometric sequences, and your student companion, we should be on page 128 to 129, but of course I could be a little off there, but that should be around where we are. As a reminder, we're going to start looking at geometric sequences. So as a reminder, this is arithmetic sequences, because the very first thing we're asking is a comparison between arithmetic or geometric. So to remind you, arithmetic sequences is when you have a sequence, a set of numbers that you are usually, there's a difference between each number. So usually it could be an addition or a subtraction between them. Okay. We had a recursive version of the arithmetic function, which looked like this, where a to the first power was the first term. So a to the n minus 1 would be the previous term, and d is the difference. And then we had an explicit formula where, again, we had our first term here, but here is where we looked at our previous information. So whatever number we're trying to find, we would subtract 1 and times that by the difference. And both of these would help us find a specific number in a sequence. What we're going to start adding on here is geometric sequence. So if you're taking notes, I would start writing this down. Let me get to a new page here. Oop, it's old stuff. Come on. Hold on. Okay, so we are going to start looking at geometric sequences, just like how linear equations, if you remember, are linear functions, and exponential functions. They had a difference. The linear function had a constant rate that was adding or subtracting, and an exponential function has a constant rate that you're multiplying or dividing. That is the similar kind of relationship between arithmetic sequences and geometric sequences. So if you look over here, this is an example here. We're going to figure out, is this sequence right here arithmetic or geometric? A geometric sequence is a number sequence in which each term after the first term is found by multiplying the previous term by a common ratio. So here we're going to now be multiplying by a specific ratio, whereas in arithmetic we were looking for the difference between numbers with a common rate or ratio. Okay? We'll just use the same verbiage here. Okay, so these kind of have similar connections, and that is why when we learned about linear functions, we did arithmetic sequences, and now that we're learning about exponential functions, we're learning about geometric sequences. Okay, so the first thing you have to do is look for a common difference or a common ratio between consecutive terms, so the terms that are next to each other. Okay, so because there's not a common difference, we know that it is not arithmetic. Okay, so when you have a common difference, then you know, so if there is a common difference, then it would be arithmetic. But if there is no common difference, because you can see if I subtract 3 and 2, that's a difference of -1. But if I subtract 4/3 and 2, that's a difference of 2/3. Then we're going to do this next thing. We're going to try dividing instead. Okay, so look for a common quotient. So they divided 2 and 3 and got 2/3. They divided 4/3 and 2 and got 2/3. And they basically divided each of these numbers in the sequence by each other, by the next number. So consecutive, meaning in a row. And when you get a consecutive answer, then you know that this is going to be geometric. Okay? So a common ratio is the fixed number that's used to find terms in a geometric system or sequence. This common ratio cannot be 0, just as a reminder, because I'm not going to be dividing. If I divide and get 0, then it's not really a sequence anymore. It's the same. We can't really divide and get 0, actually. You can't divide and get 0. If I divide and get 1, then it would be the constant number. But that's just kind of a study tip there. So Here we're going to look at a new one. Is the sequence arithmetic or geometric? So I'm going to look over here and I'm going to start to compare the two. So I'm going to go, okay, 4.5 take away 3. Is there a common difference? So 5 take away 0 is 5. This is 1.5. 6.0 take away 4.5. Okay. Yep, I got another 1.5. Okay, this looks like there's a common difference. So my estimate would be it is arithmetic. So if I look at this and I'm subtracting, you're going to get 1.5 every time. So therefore it is arithmetic. So go ahead and try these two on your own. You're first going to try and check, do they have a common difference? If they do, then you're going to go ahead and say that they are arithmetic. If they do not, if they have a common quotient by dividing, then they are geometric. All right, moving on to an example 2, we are going to start writing new formulas, recursive formulas for this geometric sequence. So just like how arithmetic sequences had a recursive and an explicit, geometric sequences have that as well. So the recursive formula for a geometric sequence, and it's over here color-coded as well as on the right of your screen, is A sub n is equal to R times the quantity A sub n minus 1. A sub n is the nth term, whatever number you're trying to find. If I'm trying to find the 16th term, that's what I'm going to put here. R is my common ratio, so that's the thing that I am multiplying or dividing by. And then A sub n minus 1 is the previous term in my sequence. So over on the left-hand side, you can start to see what that looks like. So you're going to find the common ratio. They're basically dividing each of the terms by each other here. So they're doing 12 divided by 8, 18 divided by 12, 27 divided by 8, 18, 40.5 divided by 27. And when they do that, they get the same ratio of 3 over 2. So you can see how they set them like fractions or like an actual ratio like you may have done in 6th grade. It's been, or maybe 7th grade. It's been a while since you've seen ratios. But you're going to set them up and reduce them all. They should all reduce down to the same equivalent ratio. That is your common ratio, which is R. Then we're going to plug it into our equation here. So I'm going to replace R with 3 over 2. And then I need to make sure that they know that my initial condition, my A1, is 8. Okay, so when you have a recursive formula, you need to let them know what your A1 is, which is your initial, condition or term. Okay, so we're going to look at this problem here. Can you find the common ratio and write a recursive formula for this sequence? All right, in example 3, we're looking at the geometric sequence explicit formula here. The formula, so we have a set of terms, it's the same terms from before. We specifically want the 10th term. So if you remember correctly, recursive formula is really good for like, I want the 3rd term, the 2nd term, a term that's really close to the beginning. Explicit formula is really good for I want the 100th term, I want the 35th term, for numbers that are really far away in our sequence. Okay, this is the formula we want to use, are the explicits, and when it's really close to the beginning, you would use a recursive. So over here, they want the 10th term, which is kind of far away. So we're using an explicit formula to find that. We have the same list of numbers as before. The formula here is A sub n is equal to the first term, A sub 1, times your common ratio, R, raised to the power of n minus 1, which is your previous term. Okay, so here they've set up the equation. 8 is my first term. My common ratio is 3 over 2, like we saw in the last example. And then notice that the exponent here is 9, and that's because we want to find number 10. And my exponent is my previous term. So if I want to find number 10, then my previous term was number 9. So I'm going to raise 3 over 2 to the power of 9 using my calculator, and then I'm going to times it by 8. This right here should look really familiar. And hopefully you're saying exponential function, because that's what it is. That's why we're tying them together. So in the end, it says that the 10th term of the sequence is 307.55 rounded to the nearest hundredth. So see if you can take that information and find the 12th term in the sequence below. They actually give you the recursive formula. Can you take the recursive and use that information to put it into explicit? Knowing that the initial condition, the initial term is 3. So they give you, just so you know, what they just gave you was they gave you the first term, which is 3. They gave you the R, because remember in the explicit formula, the number in front of those parentheses is R. So we know that our common ratio is 6. And they told you need to find the 12th term. So can you put all of that together? Over here, I tried to write it out. I know it's in light gray, but if you put it all together, does that help you answer your question? I'll see if I can write over here. So my term I'm trying to find is 12. My initial term is 3. My common ratio is 6. And so what would my previous term be? And see if you can solve. All right, example 4 is just kind of connecting the exponential functions and geometric sequences like we just saw on the other page, how they do end up looking very similar, the explicit formula version. So if you have this problem of the number of subscribers to a blog doubles each week, how can the trend in subscribers be modeled? We know that the number of subscribers doubles, so an exponential function would model this situation because we're multiplying, not adding. The initial number of subscribers is 5 from the picture, and we know it's doubling each week. So 5 is my initial value. My base here is going to be 2 because I'm doubling each week. X would be the number of weeks since the blog started, considering the week it started 0. We can also model this as a geometric sequence with the same formula, basically. You still have 5 as your initial value, and your common ratio from when you go from 1 week to the next is 2, multiplying by 2, which means that our exponent, instead of just being x, is just going to be our previous term. So the number of subscribers changes by a constant ratio, so both an exponential function and a geometric sequence can model this situation. So what they want you to do here is basically take the information from the previous question, take that explicit formula that they had, plug in the information for this new problem, meaning how many subscribers will there be in week 9 if the initial number of subscribers is 10. So we have a new initial value and we have a new nth term we're trying to find. See if you can use that to help solve using the explicit formula. All right, and then this last problem is always kind of those word problems applying our information. So here we have a number of people attending an annual town international food festival has decreased 20% each year since the first year. Okay, so it decreased here, decreased. How can the attendance for the first 5 years be modeled? Okay, so here's the information on the flyer, and we want to model it. So because we're decreasing a certain percentage, you can compare this to our growth model. Do I have growth over here? Here, right? Growth and decay. So I can compare this to a decay, and I'm going to find my decay factor using the decay rate. So over here, because it's declining at a constant rate of 20%, we found the decay factor by doing 1 minus R. So 1 minus 20% makes 80%. And then they took that information, and they are plugging it into a recursive formula, using R is the decay factor, R is the common ratio, which is 80%. And then they're going to find it. So now it says the recursive formula is this. A sub n equals 8/10 times A sub n minus 1, where the attendance at the first festival is 1,250. So this is your criteria here, showing your initial condition. Now we're going to have the same decreasing thing, but what if the trend continues? What will attendance be in 10 years? So instead of plugging it into a recursive formula, because I want to find a pretty big number like 10, I'm going to plug it into an explicit formula, We still have the same common ratio of 8/10. We have an initial value of how many attended last year, and we want to know how many in 10 years.